Yes, welcome. For those of you that has just joined us, I was just sharing with everyone that today we will be covering discrete random variables, binomial distribution, and normal distribution. This is really for year 2 students, right? It's sort of like a mid-year check-in / revision. By now, most of your schools would have completed at least up till binomial distribution. And if you're year 1 and you're just interested in studying ahead, I welcome you as well. But I think most of you here would be year 2 lah. Yeah. Let me also start off by introducing the brand. So a little bit about us, right, at Overmark. We are actually a learning platform, and we are created by tutors for students. So we are made up of a team of about, I think now 11 or 12 tutors. And we really try and cater our services to students, right? We offer one-on-one private tuition, but we also do like group tuition or like crash courses. And then we actually have an upcoming crash course. You can sign up at our website, but I'll talk more a bit about that later. If you haven't already, also feel free to join our Telegram channel, right? Where we usually post like all the upcoming events, and then we broadcast like sessions like today's session, right? The free mid-year revision session. We also have your free notes on our website, or sometimes we put them on the Telegram channel. So you can feel free to download those free notes over there. And follow us on Instagram as well, right? If you want to stay updated on like the different events that we are having. Yeah. Okay. So for me, sorry, not for Daryl, for me, my WhatsApp number is over here, and then you can contact me on Telegram, or you can find more information about me on the Overmark website. But basically, I am a A-levels mathematics tutor. So I tutor H1 and H2 mathematics, year 1 and year 2. That's actually what I prefer to specialize in. Do I teach secondary school math? Yes, I do, but I really prefer to teach JC math, right? Because I find it more fun. A little bit more about me. I am actually from NUS. I recently graduated with a bachelor's in engineering, and I have been teaching mathematics now for about 5 years. Yeah, so that's all about the brand and myself. If you have any questions throughout this session, feel free to put them in the chat. It doesn't have to be about like the work, right? Like math. It can be about anything really, and I will answer questions, whenever I can or at the end of the session. Today, as I said earlier, we'll be doing DRV, binomial, and normal, right? You don't need anything, like you don't need your text, like your notes or whatever it is, right? You just need your pen, a paper, and your graphing calculator, because we will be doing some practice questions. And I do believe that for math, it is the easiest and the fastest way to learn. It will be to do, right, and try the questions. And it's really about application, how you apply the concepts that you've learned in the classroom into the questions in the exam or your worksheets, whatever it is. Yeah. So yes, doing a very high level overview of the theory, but also focusing a lot on the practice questions. And I would really appreciate if you guys can answer me on the chat, because this is a more interactive session, right? And I'll be looking out for that lah. Yeah. Okay, so let's get started. Okay, I just want to caveat, sorry, one more thing. I just want to caveat that for today's session, right, the focus will really be on like what are the important things for these topics. And I won't be going like super into the nitty-gritty details, right, of the respective topics. It's really like focusing on what's important for the exam and for the questions that you have, because we have such little time, right? Yeah. So without further ado, let's get started. When we'll start with discrete random variables, okay? Some schools teach this together with binomial theorem. So if you find this a bit new, that's because your school probably taught this just packed together with the binomial distribution chapter. But what is discrete random variables? I guess before we even go into what are discrete random variables, and then the opposite, not really the opposite, but another type of random variable is continuous random variable, right? What are those two? you should know what a random variable is. So a variable is something that you are measuring in, like, for instance, an experiment or in a population. Usually it's like the number of, let's say, phone calls in a minute, or the lifespan of like a light bulb, right? So something that you are measuring is a random variable. And for discrete random variables, right, the emphasis is that for discrete random variables, whatever you are measuring is actually countable. Okay, so the example would be very apt, right? Which is, for instance, the number of phone calls, right, we receive in a minute, let's say. Okay. And then, I want to talk a bit about also, because we can't talk about discrete random variables and not talk about continuous random variables, right? Okay, so what are continuous random variables? I'm just going to write here. Versus, okay, we have continuous random variables. And this is when whatever you are measuring actually happens in a given range, right? So discrete random variable would be countable. Continuous random variable would happen in a given range. And I'm going to give you an example. So for instance, previously what I said, right? Like the lifespan of a light bulb manufactured in a certain factory, for instance. And the lifespan of like the light bulbs in a factory can span from, like, let's say 1 week to like 1 year, right? Your answer can fall within this whole range of values. That's when you know it's this continuous random variable. And for A levels, right, your continuous random variable actually corresponds to your normal distribution. And your discrete random variables corresponds to your binomial distribution. So use this as a guide, right? Right, the countable versus given range, right? Use this as a guide to help you understand exactly in the question, are they talking about a binomial distribution or a normal distribution, right? Think about whether or not you are able to count whatever you are about to measure, and that should help you identify, because one of the biggest mistakes that a lot of students make in the exam, right, is they sort of take this like question that's supposed to be a normal distribution and they take it as a binomial question, and then they get the probabilities wrong. Okay, so that's an overview of discrete random variable versus continuous random variable. And when we think about our random variables, right, discrete random variables, we think about two parameters, right? Two very important parameters that we try and measure. So the first one would be the mean, or what we know as the expectation. And the second one would be the variance. So let's take a look at the mean first, or expectation. Okay. This is also known as, This is also known as your mean, aka your average, right? It's the average of all the values. Okay. So let's say, okay, you are trying to find the mean of two different occurrences. Okay, so let's say we have expectation of 2x. That would just be 2 times the expectation of x. Or let's say we have expectation of two independent, right, occurrences. That will just be 2 times the expectation of x as well. So you realize that for the mean, whatever happens to the variable, right, happens for the mean as well. It's very straightforward, right? So over here, let's say we have the expectation of a constant. It will just be the constant itself. So a good example would be like your expectation of 2 would just be 2. Okay. And then this would correspond to this. Your expectation of, let's say, 2x will just be 2 times the expectation of x. If let's say we have two independent occurrences, scenarios, then that would be x1 plus x2, and it would still be 2x. Okay. So this is different from, let's say, if you have expectation and this is squared, then the formula over here would change. And what does this formula mean? We will take a look later. Okay, but basically, for discrete random variables, you're going to have to use your probability distribution table. So this is going to be super useful for this chapter, right? A bit linked to your probability. And I'm not sure whether you remember, but your probability distribution table more often than not looks like this. And then we have the different values over here. So usually we have x here, and then the probability of x being x over here. So these are all the possible outcomes. And then these are your probabilities. So in the probability distribution table, all these probabilities should add up to 1. Yeah. So you list all your different outcomes, and then based on the question, find the different probabilities. And from here, you're able to find the expectation, right? That is what this equation is saying. It is the summation of the outcome times the probability. So in order to find the expectation, you take this times this, and then this times this, and you add all of them together. And we're going to do an example later to illustrate this, okay? So this is for expectation, which is really just your mean on average. You just need to know this formula and how to manipulate with the given different situations, okay? For your variance, okay, I know in many of your notes, there's like so many different equations, right? The most important equation that you need to know, right, is really just over here. The variance is actually the expectation of x squared, and that's what we saw over here, right? Expectation of x squared minus the expectation of x squared, right? The expectation of x squared, so mu squared, okay? And for variance, it's very special. Okay, so it's very different from expectation. For the variance, if you find the variance of a constant, it's just going to be 0. Okay, what is variance actually? Sorry, I keep saying this, right? But variance is actually your standard deviation squared. Okay. In other words, it's your sigma squared. Okay. And it is also like a measure of the spread of your data. From your mean. So how spread out is your data? All right. So this is the formula. And okay, that's why for a constant, which is just a number, right? A constant number, the variance is 0 because 2 is just going to be a 2, right? For variance, it's very special because over here, right? If let's say you have something multiplied by the variable inside here, you're going to have the square this inside. So let's say, okay, examples would be variance of 2x will then be 2 squared the variance of x. As long as inside here is a multiplication, then this will happen. Variance of 3x will be like your 3 squared variance of x. So on and so forth. Okay? Versus, if let's say, So this is like if you double count the same occurrence, right? 2x. It's the same for your mean, by the way, okay? So we're gonna take a look at examples later to see the difference. But let's say you have your variance and you have two independent occurrences, x1 plus x2. That would just be 2 times the variance of x. So it's very important for you to know the difference. This and this, okay? So something to note is that, remember, no matter what, right? Okay, you always add variances together, regardless of whether over here inside, right, it's a minus. You always add your variances together. You never ever minus it off. Okay. So just now what I was describing is over here. These are the most important results for this chapter. And this chapter is super duper short. Okay. So let's try an example over here. I think this is talking about like the first part of your, as in this question is talking about the first part of your discrete random variables, where like we figure out how to find the expectation and variance. Later on, we'll see what we mean by manipulating like the expectation and variance, right? To be like x1 plus x2 versus like 2x. What's the difference? Okay. So have a read this question and then we'll go through it together. Just gonna change my colors. Okay. So I'm gonna give you guys a few seconds to just read through the question, and if you want, you can start attempting it. Okay. So 5 fair coins are tossed together in one throw. Okay, so that means you grab like 5 coins and you just throw it all together. The number of tails and heads obtained in one throw are denoted by T and H respectively. And X denotes number of tails minus the number of heads. Show that this X is equal to 1, right? With the probability of X being equal to 1 is 5/16. And hence find the probability distribution of X. Okay, so let's slow down, right? Okay. What do we mean? Okay, by probability of X equals to 1. Okay, so let's analyze the data first, right? Let's analyze the question first. If you look over here, right, they toss 5 fair coins. It's either, right, okay, there's 2 spectrums, right? It's either you get all 5 are heads or all 5 are tails, and then there's many things in between, right? It could be 4 heads plus 1 tail, right? 3 heads plus 2 tails, so on and so forth, right? There's like different outcomes, but basically if we do, let's say 5 heads or 5 tails minus 5 heads, then the possible outcomes for my X, right, my small x, and they ask me to tabulate the probability distribution, right? This actually means the table, okay, that we drew earlier on over here, this purple color table, okay? So when they say find the probability distribution, you are supposed to find that table, okay? So what would that table look like? It would look like this, right? Where we have your X and your probability of X being X, okay? So what are all the possible outcomes? That's what we're trying to find out here, right? If let's say I have 5 heads and 5 tails, correct? So 5 tails and 5 heads, right? It would be 5 minus 5. So one of the possible outcomes is actually gonna be, okay, it's not possible for you to get 5 tails and 5 heads at the same time. But one of the possible outcomes is gonna be that you have, okay, I'm gonna write out the different scenarios over here. Realize that this table is too small. So just to make it clear for everyone, let's write out all the different scenarios. Remember, it's not possible for you to have 5 heads and 5 tails at the same time. If you have 5 heads, it means that you have 0 tails. And if you have 5 tails, it means that you have 0 heads. Oops. Okay. So the first possible outcome will be, let's say, okay, you get 0 tails and 5 heads. Okay, that means you get 0 minus 5. So inside here, that would be seen as x is equal to minus 5. In other words, right, this probability would be written as probability of x being negative 5, which is a bit special, right? We don't usually see this. But for this case, because they have defined t minus h as such, therefore we can say 0 minus 5, right, will be minus 5 over here. Okay, another possible outcome would be what? If I get 1 tail, and then that would be 4 heads. So 1 minus 4 would be minus 3. Okay, if I get 2 tails and 3 heads, that will give me a minus 1. If I get 1 tail and 4 heads, that will be a minus 3. And of course, oh, sorry, I already put in the minus 3 at the, over here, at the second box. Okay, so again, now we have 0 tails, 5 heads, 1 tail, 4 heads, 2 tails, 3 heads. What other outcomes are there? There is going to be your 3 tails and then 2 heads. Then that will be a positive, right? 1. 4 tails, 1 head. That will be a positive also, 3. And then we have your 5 tails. Oops, this is so ugly. 5 tails and 0 heads. So that's your spectrum, right? That's all the possible outcomes. And for this, your outcome would be 5. I'm going to erase this last part over here. Okay, so this is what your probability distribution, all the possible outcomes will look like. Now it's up to you to go and find the actual probabilities, right? So how do we do that? Let's start with, because they asked us to show probability of x equals to 1, right? Correct, which is this over here. So let's start with this. Okay, just so we can sense check ourselves. And they told us that the probability of x being 1 is actually 5 over 16. Yes, okay, so someone asked, can we use P and C? You definitely can, okay? But for this case, I'm gonna use probability, okay? Because it's much easier, it's less tedious. But it's actually more or less the same thing, okay? So let's take a look at how we're gonna do that. Okay, so before that, we know that it's fair coins, right? Correct. So your probability will be half lah. Probability of tossing a head or tail either way will be half because it's a fair coin, right? So the probability of x being 1, right, would mean that I have 3 tails and 2 heads. Correct? So let me just write over here. Okay. So the probability of x being 1 will be probability of me having 3 tails and I minus 2 heads. Correct? So over here, you're going to use a combination of probability and P and C. So my 3 heads, right? Correct? My probability is actually half times half times half, correct? Which is half cubed. Because the probability of me getting a tail is half. Then for my 2 heads, it's also going to be half, right? So times half squared. But I have to take into account the order, right? Which, am I going to get a tail first or a head first? That's why I have to times my 5 factorial. And because I have sort of repetition, right? 3 heads and 2 tails, I'm going to divide by my 3 factorial and 2 factorial for the 3 heads and 2 tails. So you can calculate this and you should get 10 out of 32. which if you simplify will give you your 5 out of 16. And then you can say shown over here. So over here, I will write 5 out of 16. Oh. Okay. So now we're going to do it for the rest of them. Okay. In fact, I want to give you guys the chance to do some of them. Okay, I'll take you through a couple more and then you can tell me what the rest are. Okay. So let's do probability of x being -5. I'm going to start from the left-hand side. Right? This would be what? The probability of there being 0 tails minus 5 hits. Okay. Which if I have 0 tails, then it's just going to be nothing, right? Okay, then the 5 hits would just be half to the power of 5, which is your 1 out of 32. And that should give you a clue, right? That for your 5 tails, that will be the same. This would also be 1 out of 32. Okay. Now let's do it for your x equals to -3. Okay. Or actually, I'll leave you to do that. Okay, because the 1 over here will be the same as this -1 over here. So this will also be 5 out of 16. Can someone calculate the one for the 3 and -3, which are the same, right? You can see that it's actually going to be symmetrical. Okay. And tell me what it is. So I'll give you a couple of seconds to try this out. What will I get for, let's say, probability of x being -3? I'll just wait a couple of minutes. If, let's say, no one is confident enough to answer, I will then run through it. Oh, thank you. Rachel said 5 out of 32 and you are correct. Good job. Okay, which means that you fully understand the concept. So what did we do over here? Okay, what did Rachel do over here? She probably did, right? Half to the power of 4 times half, correct? Times your 5 factorial to choose which one you got first, divide by 4 factorial because you have the same like 4 heads or 4 tails. Okay? So with that, you would have gotten your 5 out of 32. So just like that, right, you have already completed the first part, proving that, you know, probability of x being 1 is 5 out of 16, done, and tabulating the probability distribution table. Now we're going to look at the second part, which is calculating the expectation of x. Now this is the easiest. Expectation of x, you just follow the formula, right? It would be this times this plus this times this, and then everything you're going to add up together. Okay? So if you go and add up, right, you're going to realize that, okay, it will be -5 times 1 out of 32. But on the other side, it will be 5 times 1 out of 32. So these two will cancel out. And then the two 3's, right, which is -3, 5 out of 32, 3, 5 out of 32. And then also your -1, 5 out of 16. 1, 5 out of 16, right? They will all cancel each other out and your expectation for this is very special. It will just be 0. Okay, so your expectation will be 0. What about for your x, your variance? Okay, so remember your variance. The formula is what? E x squared minus ex, the whole thing, squared, right? This is your formula. So you already have your EX whole thing squared, which is just going to be 0 squared, which is just 0, right? Now your job is to find EX squared, literally EX squared, okay? So what will this be? You have to use again this table and tabulate, right? Okay, what is your x squared? So I'm going to move this part away to the bottom. And I'm just going to write one row, right? With the x squared. Oh. Yeah. Okay. So one more row with the x squared, like that. So what is x squared? It will be 25, 9, 1, 1, 9, and 25. Can you see? -5 squared will be 25. -3 squared will be 9. So on and so forth. Okay. So how you tabulate this EX squared, right? Is the same as how you would tabulate your EX. Okay. It's just using now this x squared over here. So it will be this times this plus this times this, so on and so forth. And you realize that you get 2 times 25 times 1 out of 32 plus 2 times 9 times 5 out of 32 plus 2 times 1 times 5 out of 16. So your EX squared, you go and tabulate, it will be 160 out of 32, meaning that your variance of x is also going to be 160 out of 32, which is actually 5. And that is your final answer. Okay, so this very nicely actually sums up discrete random variables and how to find your variance and your expectation. Okay. Again, we're going to do more examples later. Okay, but now want to move on to your binomial distribution. Okay. So this is where the more interactive part comes, right? Okay. Binomial distribution, the very first thing that you guys should have learned in school is the conditions to satisfy a binomial distribution. So can someone type in the chat, right? What are the conditions for binomial distribution to hold true? What are the conditions for a binomial experiment to hold true? I'm going to give you a clue. There's 3. Can someone tell me what's the first one? 2 outcomes. Thank you, Rachel. So each trial, right, only has 2 possible outcomes, and that is your success or failure. Okay. And then ZX said independent. Okay, thank you. Very good. Okay, so that's the first one, right? Experiment consists of n number of independent trials. And then what's the last one, guys? Probability of success of each trial is constant. Yes. Thank you, guys. Well done. Okay, so that's the third one, right? Probability of success of each trial. Okay, and for this case, denoted by P, right? Because I want to define something later. Remains constant. Well done. So these are your 3 conditions for a binomial experiment. And you have to memorize them because sometimes they ask you this in the exam. Okay. Before moving on, just want to ask if you guys know what it means when I say independent trials. What does independent mean? Independent is like if, okay, so I know in probability, and I know I'm not covering this chapter, but I just want to briefly touch on it, right? In probability, we have learned this word mutually exclusive. And then we have your independent, right? So what does independent mean? It means that the outcomes don't affect one another. Okay? Versus mutually exclusive means that the two events cannot happen at the same time. So if you look at a mutually exclusive Venn diagram, right, that will look like this. There's no overlap. So the probability of A intersecting with B is just going to be 0. Okay, so they cannot happen at the same time, mutually exclusive. Examples of this would be, you cannot be like, for instance, in the bus and at home at the same time. That's impossible. So those are mutually exclusive events. They can never happen together, right? But for independent events, correct, the outcomes don't affect one another. So what would be like an example of a non-independent event? Let's say I have like a deck of cards and I take out a card, correct? And let's say my definition of success is like if I get a king, okay? So I take out a card and it's like the 4 of hearts, okay? And then I ask you to pick a card. Are those independent events? No, because I already took out one card. That means your probability, right, of taking a king is higher now, for instance. And that changes the probability, and that means it's not, the events are not, they don't exactly not affect one another. They do affect one another because I did not replace the card, right? But if let's say I took out the card, right, I got a 4 of hearts, that means I didn't win. I put it back in and I shuffle the deck again and I let you pick a card, then yes, it means that they are independent events because you still have an equal probability of that happening. Okay, so I hope that is clear and illustrates it well. Okay, so this is your 3 conditions that you have to remember. And for binomial, right, correct, usually, okay, for binomial and actually even for your normal, right, you have to define random variable. Okay, so let the random variable x be, let's say, the number of successes, the number of like hits obtained out of how many like experiments you're doing, like out of 5 like outcomes, for instance, right? Okay, so your binomial distribution will be as follows, right? This is the magic equation that you will be writing. X follows a binomial distribution, and then your n is the number of outcomes. And then P is your probability of success, whatever you define success as lah. Okay? And for binomial distributions, another 2 important equations to know will be your expectation of X is NP, and the variance of X is NP1 minus P. Literally taken from this over here. All right. So in essence, this is actually all the things that you need to know for this chapter. Okay. I'm going to move on and talk about normal first, right? And then we're going to look at the different questions. Okay. So for normal distribution, a couple of things. Okay, usually for normal distribution, it's for like when your n is like very, very, very large, like you have so many outcomes, right? That it's very difficult to count. Okay. So, and over here, when we say n is large, right? In statistics, n is large. It's like n is more than 30, that kind of thing. Okay. So for normal distribution, let's say you define random variable x follows a normal distribution. Usually we put here the mean, the mu, and then sigma squared, which is your variance. So this is your mean. Which is what we learned just now, right? Correct? And the variance. Okay. And of course, for your sorry, my grandmother is what I will see. And of course, for your random variables, okay, then it follows what we talked about just now, right? Over here, your mean and variance, right, will be affected as follows. Over here, remember we talked about how if let's say it is, especially for your variance, that's the one that differs. If let's say it is like nx, then it will be n squared x, variance of x. If it's x1 plus x2, it will be the two you add together like that, for instance. Okay? So over here, I'm just going to write a summary table for you, okay, comparing x1 and x2 versus your 2x, because this is especially important for your normal distribution. Okay, so let's do it together. So we have your mean, your variance, and then I will consolidate with the distribution later. Okay, so let's say you have two independent events, right, that are identically distributed. That will be x1 plus x2. Versus if you have twice the value of one observation. Okay, so again, this is two independent events. And this is twice the value of one observation. Yeah. So what will these values be? I'll use blue color. Okay, so the mean will just remain, right, as 2 times the expectation of x. This is also 2 times the expectation of x. Okay. The variance, this one will be the variance of x1 plus x2, which will be 2 times the variance of x. And this will be the variance of 2x. And then this would be 2 squared times the variance of x. So you see, throughout the whole of statistics, this concept is very important. Okay. So the distribution ends up being your x1 plus x2 follows a normal distribution of 2 mu and then 2 sigma squared, versus over here, it will be 2x follows a normal distribution of again 2 mu, but this time it's 4 sigma squared because of your 2 squared over there. So this is in general what we want to emphasize over here. Okay. And of course, for this chapter, you need to be able to use your GC very well, both for normal, binomial, actually the whole of statistics, right? You need to know how to use your GC very well. So I'm going to give you a actually overarching summary also, right? If let's say you are finding, okay, the probability of, let's say, x being equal to something, for this, you use your binomial PDF. Let's say you're finding x is less than or equal to something. This would be binomial CDF. Can? Okay. For normal distribution, we use mainly normal CDF to find probabilities. Okay, to find probabilities. And there's different question types, right? Let's say, okay, you want to find, okay, so we have a scenario where it's like probably you're asked to find the probability of x being less than or equal to, let's say, m. And this is actually what you are finding. You are finding m. Right? To find m, you will use your inverse norm. Okay. And okay, usually for binomial, we only have like this less than or equal to. But for normal, right, you have like your left tail, right tail, and center. So it's very easy to remember. Like your left tail just means it's less than or equal to. Your right tail, you see where it's pointing to, more than or equal to. Then your center is just equal sign. That's all. Okay. So this is if you're using inverse norm. Okay. And then another big concept in normal distribution is actually your standardization. Okay, your standardization. So standardization, right, usually happens when you don't know your mu or your sigma square, or let's say your, usually these two, your mu or your sigma square. Okay, so what happens when you standardize, okay, is initially you would have your normal distribution, right, correct, being mu and sigma square. When you standardize, okay, this becomes, and this is true for anything, right? If after you standardize, it becomes mu will definitely be 0 and your sigma square will definitely be 1. Okay. So, but when you standardize, what you're doing is you're going to define your z, okay? This z over here, sorry, so ugly. Your z over here, this becomes x, right? And that's from your original x over here. Okay, it follows this x, okay? Oh, actually, what's inside lah? Okay, not exactly this. Later I show you. X minus mu over sigma. Take note that this is sigma and not sigma squared. So you will change it to help you find whatever you are missing, either the mu or the sigma. Okay, so that's more or less it. Now let's take a look at the examples. We'll do a couple. Hopefully we are able to sort of put this theory into practice. Okay, so let's start with this question. I'm again going to give you some time to read the question, and you can start doing if you are confident. Okay. So this actually is a lot of this question, right? Still has your DRV involved. Okay. So let me get into it. Okay. An electronic device contains 5 components, 2 of which are faulty. To isolate the faults, the components are tested one by one until they are identified. The random variable x denotes the number of tests required to locate both faulty components. Show that the probability of x being 3 is equal to 1 out of 5. Okay. So, and after that, you're supposed to find the probability distribution of x. Okay. So first of all, I'm gonna define. Okay, I'm gonna let f be the event that the component is faulty, and then n be the event that it is not faulty. Okay, so for this particular probability that they're asking me to find, right? Probability that x is 3, there's only a few possible outcomes, correct? So x denotes the number of tests required, right? So if I only have 3 tests, then, and for me to denote that it is faulty, correct? And then we look at what they define again, right? There are 2 faulty components. So it's either I get the faulty, not faulty, and then the faulty, right? So this is the case 1, scenario 1, faulty, not faulty, and then faulty. This is scenario 1. Case 2 is what? I get the not faulty, and then faulty and faulty. And that's my only 2. Why? Because can I get a third case that is faulty, faulty, not faulty? No, right? This is impossible. Because if I get a faulty and faulty already, then my test would stop. That means my x will be equal to 2. That's why this is not possible. Okay? So for the probability of x being 3, therefore I'm only looking at these 2 cases. And then what would my probability be? Okay, so the probability of 2 of which are faulty, right, in the 5 components, correct? So that means I have 2f, 2 faulty, and I have 3 not faulty, right? So if I get a faulty first, correct? If I get a faulty first, that would be 2 out of 5 times not faulty is 3 out of, then there's 4 left because I already took out the faulty. And then there will be 3 left, but there will be 1 faulty left. So 1 out of 3. So this will be faulty, not faulty, faulty. Plus Not 40, I have 3. So 3 out of 5. 40, I have 2 out of 4. Then 1 out of 3. And this is not 40, 40, 40. So just like that, you'll be able to calculate your probability and verify that this is equal to 1 out of 5. So you can say shown. Why is n not included? Good question. Okay. So remember, x, right, is if let's say you have located both the 40 components. But if you put n, then it does not mean that, you know, in 3 outcomes, you were able to locate the 240 components. That's why n cannot. Because you technically did not succeed, and you will take 5 outcomes because you will do n, and then f. So only after you have found the 240 components, then your experiment is considered as ended. Ken, does that answer your question? Okay. So with that, let's tabulate the probability distribution. Okay, so I will help to draw the table. Okay, let's think about what are the possible outcomes. So we have x, probability of x being x. Okay, so what are the possible outcomes? Obviously, we have 3, right? Correct. Over here. Can your x be 1? No, right? Because remember, the experiment only ends when both the 40 components have been found. And there's 240 components. So x being 1, right? You find 140 component, right? It's out. Okay, so the minimum is what? 2. And then, of course, we have your 3, 4, and then maybe you take all 5 lah. Huh? Maybe you take all 5 selections to find out that something is 40. Okay, and we know that your 3 is already 1/5. Okay, so I'm gonna do the one for number 4 with you guys, and then you guys can do number 2 and 5, and then let me know your answer. Okay, so for the probability that x is equal to 4, okay, what are the possible outcomes? Okay, so number 1 is, let's say we have not 40, and then 40, 40, right? So only at the end, then I find my 240 components. The other one is what? I find not 40 first, then 40, but then I find not 40 again, then I find my 40. Another one is you start with 40, and then you find not 40, and then you find another not 40 and a 40 over here. So actually, these are the only 3 outcomes, because what are the ones that you cannot have, right? For instance, can you have 40, not 40, and then 40 and not 40? No. Right? Because remember, it will have n here. So for this, your x will have been equal to 3. There's 3 possible. So must think of it very logically. Okay, so you only have 3 possible scenarios, correct? For x equals to 4. So let's find this, right? Sorry. Okay. The probability of x being 4 will be, okay, not 40 is, there's 3 components, right? Yes. Will be 3 out of 5 times 3 out of 5, sorry, not 3 out of 5 anymore. 3 out of 5 times, and then I'm left with 2 not 40 out of 4 times 2 out of 3 times 1 out of 3. This is for the first scenario. Second scenario, I have 3 out of 5 times, again, I have 240, right? So 2 out of 4, but I have 2 not 40 left. And then the last scenario is my 40 is actually 2. So 2 out of 5 times 3 out of 4 times 2 out of 3 times 1 out of 3. So you can go and add all this together, okay? And find that this is 1 out of, sorry, not 1 out of 3. 3 out of 10. Okay? So very systematically, just do it like that. Okay. Would you guys be able to find the one for 2 and 5 for me? So y'all can just try. What would the one for 2 be? And what would the one for 5 be? Let's start with the 2. Probability of x equals to 2 would be what? I'm just going to give a couple of minutes for those of you that want to try. The one for 2 is super easy. So the one for 2, there's only 2 possible outcomes, right? Correct? Which is, there's only one possible outcome. Sorry, someone is asking, can we use PNC to find out the different probability values? Yes, you can. You definitely can. But yeah, I think the PNC way is a bit more complicated, in my opinion lah. Yeah, but you can definitely find using PNC. Okay, so for the one for 2, right, would just be one outcome, right? Which is just you get 40 and 40. So that's just going to be 2 out of 5 times 1 out of 4, which is 1 out of 10, right? It's the one for 5 that's a headache. So what are the different scenarios for the one for 5, right? It would be, let's say you get all your 40 at the end, right? That's one scenario. Another one is if you get 2 40s, two not 40s, and then a 40, and then a not 40 and a 40 again. So it only ends at the end, right? Number 3 would be if you find a 40 in the second one, but then the last 2 are not 40, and then the last one is 40. And then the fourth and last scenario would be 40, and then in between is all not 40, right? Until you find a 40. So you can slowly go and calculate the probability for this, but in interest of time, I'll tell you that this would be 2 out of 5. So with that, you will have tabulated your probability distribution table for part 1. Okay. So let's do part 2. Find the probability of x1 being 3 given that x1 plus x2 is less than or equal to 5 if x1 and x2 are 2 independent observations of x. So for this, okay, it's like a mix with like your probability, right? Correct. So probability of x1 being 3 given x1 plus x2 is less than or equal to 5 is actually what? Is actually the probability of x1 being 3 and x1 plus x2 is less than or equal to 5 over the probability of the second one, right? Which is x1 plus x2 being less than or equal to 5. So this is from your conditional probability, right? the probability chapter. Okay, so now let's think of it, right? Okay, when will my probability of x1 be 3 and my x1 plus x2 is less than or equal to 5? So if my x1 is 3, right? Correct. It means that my probability of x1 is 3 already. So my x2 has to be what? In order for it to be less than or equal to 5, and I know that my x cannot be 1, right? Correct? You see over here in this table, it's impossible for my x to be 1 because I have two faulty components, remember? So I know for sure then that this will be a 2. Over, okay, then now this part, x1 plus x2 less than or equal to 5, I need to analyze, right? Okay. It's either I get probability of x1 being 3, x2 being 2, or it can be probability of x1 being 2, x2 being 3, right? So you add them together is equal to 5. Or it can be what? Is there anything else? Less than or equal to 5, so it can be 4 also, right? Correct. So it could be probability of x1 being 2 and x2 being 2 as well. And if let's say x1 is 2 and x2 is 2, then it's the same thing lah. So we don't need to double count that. Okay. So with that, using this, we'll find our probability. Okay. The probability of x1 being 3 and x2 being 2, right? Correct. So let's see x1, right? I have 5. Okay, actually, I don't even need to go and recalculate because I already have all my probabilities here. That's the beauty of it, right? So probability of x1 being 3 will just be 1 out of 5. And the probability of x2 being 2 will just be, you see 2, 1 out of 10. So it'll be 1 out of 5 times 1 out of 10. Over, and then what is x1 being 3? 1 out of 5, and then 1 out of 10 also, right? Again, and then this would be x2 being 2 first, 1 out of 10 times 1 out of 5, correct? And then the last scenario will be 2 and 2, which will be 1 out of 10 times 1 out of 10, using a probability distribution table. So go and calculate this out, right? Okay, and you should get 2 out of 5 as your final answer for your probability over here. Then let's look at the last part. The cost depends in part on the number of tests required and is given by the formula 10 plus 3x. Okay. Find the variance of C. Okay. So the variance of C is linked to the variance of X, right? Correct. Because you see, the variance of C would be based on this over here. Okay. Would be what? 10 is a constant, so I don't add it in. Okay. It will be 3 times. Is it 3 times the variance of X? No, right? It's 3 squared the variance of X. That would be my variance of C, which means that it will be 9 times the variance of X. So in order for me to find my variance of C, I need to find my variance of X first. Okay? And to do that, I need to find my expectation first, right? Correct? So this will be part 3. Okay, my expectation of X, I will just use my probability distribution table here. 2 times 110 plus 3 times 15 plus 4 times 310 plus 5 times 25, right? Go and calculate this out. You should actually get a 4. Then to find your variance, you have to find what expectation of X squared, right? This should be second nature to you by now. So it will be all this, right? Okay. Wait now. okay? But all the constants would be squared, 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 and squared over here. Go and calculate this out, right? You should get 17. So what is the variance of x? It will be this 17 minus your 4 squared, which is 1. Therefore, your variance of C will be 9 times 1, which is just going to be 9 over here. And that would be the end of this question. Super long, right? But yeah. Okay. Oops, sorry. Okay, we didn't even need this part. Now let's look at this final question over here. Okay, before we call it a day. So, okay, I'm going to give you guys some time to read the question. Okay. Oops, sorry. On average, 40% of Christmas tree light bulbs manufactured are red and the rest are blue. So if there's like 10 red, right? Then that means there is total amount minus 10 blue, right? Okay, so the lights are sold in boxes of 20. So in a box, if there's 10 red, then that means there's 10 blue, right? Assume the number of red light bulbs in a box has a binomial distribution. Find the probability that a box of 20 light bulbs contains fewer red light bulbs than blue light bulbs. Okay, so your red has to be less than your blue. You're supposed to find this probability. Okay, how do you even start doing this question? Okay, this one is a bit tricky. So let's go through it together. First of all, you're going to let random variable x, okay, be, let's say, the number of red light bulbs. Sorry, so ugly. Okay, which means that x actually follows a binomial distribution of what? There's 20, and the probability of you getting a red light bulb is 40%, right? So it's 0.4 over here. So can you see that, okay? The number of red light bulbs, right, is x, right? Correct. That means the number of blue light bulbs in a box will be 20 minus x. So that means that the probability of my red, which is x, being less than 20 minus x, which is the blue, right? Correct? This is what I'm trying to find. And how do I do this? I'm going to simplify it. Okay. This can be probability of 2x being less than 20, which is the probability of x being less than 10. And then, because your binomial, you cannot just do less than, you must do less than or equal to, a bit annoying, but yes. Then you must do x is less than or equal to 9. And then you use your GC, right? This is just normal. Normally, like you calculate your binomial CDF, okay, for less than or equal to 9. And then you have your N and P over here. You should be able to find. Can someone help me find? So that I know that I'm not alone doing this. Or that rather that you guys are learning. What will the probability be? Anyone? This is just plugging into your GC. Okay, yes, thank you. Thank you, everyone. Okay, it's 0.755. Okay. Then for part 2, right? So after doing all that, you get 1 mark. Okay, it's okay. Okay. Then part 2, in n randomly chosen boxes, the probability that there will be at least 2 boxes with fewer red light bulbs than blue is at most 0.99999. Okay, so find the greatest value of n. So now you're trying to find n. Okay, so for this, actually, you must recognize that it is a binomial distribution as well, okay? And it's a new binomial distribution. So you're going to let's say, let y, right? Let random variable y be, because this time you're counting what? Number of boxes, right? With fewer red than blue light bulbs. Okay, so in the exam, please write out the whole thing. Okay, so you're finding the number of boxes with fewer red than blue. Okay, so this y follows a binomial distribution, and you don't know what is your n, right? Correct, but you know from your first part that the probability, right, of you getting fewer red light bulbs than blue, right, is 0.755. So that is what you will use here. Okay, but you'll use the longer version like that. Okay, to more SF so that it will be more accurate. Okay, and what did the question say? They say the probability that there will be at least 2, so more than or equal to 2 boxes with fewer red than blue is at most 0.99. So how is this represented in the equation? Probability that your y is more than or equal to 2. This is at most, so it's less than or equal to 0.999. Again, for your binomial, you cannot do more than, right? So 1 minus probability of y being less than or equal to 1. Then you manipulate and simplify. Okay. So this is what you should be calculating. But can you use your binomial CDF? It's difficult to, as in you can, as in you are supposed to, but you realize that you don't have your n to put in, right? So when you have unknowns like this, you need to put this, your binomial CDF, right? Correct? Into the graphing part of your GC. So you click the top left where it says like y equals 2, then you go to like the different graphing equations, right? You put in, okay, the binomial CDF, okay, where your n will this time be your x, your p will follow, right? 0.755337. And then that will be 1. Okay, your x value is equal to 1. Okay. So by putting this into the graphing part, right? Okay. Then you can go to the table. So now you should be going to the table. Okay, and at the table, right, you will say, okay, you will observe. So then you'll write in your exam from GC. When your n, correct, is this going to be a table, right? When your n is 6, 7, and 8, okay, your probability, which is what you are calculating over here, right, from the table will be 0.00419, 0.00119, 0.00033. And they're asking for the greatest possible value of n. And you see over here, because your distribution actually follows like that, right? It goes up and then down. And you realize that over here, right, it went up and then it went down again, right? It went down. So the greatest possible value of n will actually be 7. Okay, so for this, it is when it's more than or equal to 0.01. So this is the greatest, this is the threshold. Because at this point, beyond this point, this is already less than 0.001. Yes, n is 7. Good job. Okay. Okay. Now let's move on to the third part. A random sample of 50 boxes is chosen. Oh dear. Okay, so this is where a bit of sampling is involved. I think that's the problem, right? Most of the questions are interlinked, like all the chapters. Okay, so a random sample of 50 boxes is chosen using an approximate distribution. So this one you have to know that it's normal, right? Because 50 boxes, your n is large. It's more than 20. Okay. Find the probability that the mean number of red light bulbs in one box will exceed 7.5. Okay. So for this, okay, because in the front, right, okay, at the front, it followed like a binomial distribution. So you can say, okay, the expectation of x, because x follows a binomial distribution, is NP, which is 20 times 0.4. And then the variance, again, because it follows a normal distribution, will be n p 1 minus p, which is 4.8. Okay, because again, binomial, yeah. X follows a binomial distribution. So you use this as your parameters for your normal distribution, right? Because for your normal distribution, these are the parameters that you need. Okay, so for this sample. So you say, okay, since, and some of you will have learned this already. Sampling, since n equals 40 is large, by central limit theorem, CLT. So this is from your sampling chapter, okay? Your x bar follows a normal distribution of 8, 4.8 over 50 approximately. So again, this is for those of you who have learned sampling already. If you have not, you can revisit this next time, okay? So the probability of your x bar will be less than or equal to 7.5, right? That's what the question is asking for. It will not exceed 7.5. You put this into your GC, the normal distribution, right? You should get 0.0533. Okay, and then the very last part, a customer selects boxes of light bulbs at random from a large consignment until she finds a box with fewer red than blue. Give a reason why binomial distribution is not an appropriate model for the number of boxes. Okay, so I'm not gonna write this out, but I'm gonna read it out. Okay, what's the reason? Why does this not follow a binomial distribution? It just means that it doesn't meet one of the conditions, right? So which condition is it? So in the context of this question, for this question, right, the number of boxes that this customer over here, right, is selecting is not fixed. In other words, the sample size is not fixed. So the binomial distribution is not appropriate because there's no fixed number of trials. Okay? So essentially, it does not follow because there's no fixed number of trials. And that's all for this question. Okay, I have one more question over here, but I wanted to leave some time for your questions. Okay, if you have any, I will be uploading this set of like notes, as in material onto the Telegram chat. So if you want to try, right, attempt this last question and send your answers in that chat, right, in the comments section, when I send this out, feel free to do so, right? I will definitely answer whether or not you're right or wrong. If I can, try and mark it on my iPad, okay? And before we end, just want to let you all know, like, as in thank you for attending the session, and I hope you learned something useful. If you found this useful, do consider signing up for our crash courses. We have it for several subjects, and you can find more information online. We also have curated notes that we're selling on the website, so feel free to make a purchase on the website as well. And of course, we are also like doing private tuition, group tuition. So if you are interested, just gonna go back up here. Feel free to contact me. My contact details are over here. Okay, so thank you everyone. I hope you learned something new. You found this session useful. And that's actually it. Yeah, you guys can leave if you have no questions, but I will stay here for questions.